Welcome, everyone. Today, we're going to talk about building an open data lakehouse using Trino and Apache Iceberg. My name is Matt Fuller, co-founder and VP of product here at Starburst, and I have with me my colleague, Tom.
Hi, I'm Tom Nass, Director of Customer Solutions here at Starburst, and I'm told that I am an all-around awesome guy. So thanks for that.
Awesome. For those that are watching, you'll see that there's a QR code. If you scan that, it will bring you to a wonderful cheat sheet for both Trino and Iceberg. So for our agenda today, we're going to start with an introduction to Trino as well as Apache Iceberg. For those of you who are not familiar with it, if you are, feel free to fast forward to the workshop later on in this recording. In addition, we're going to talk about how you can use Trino and Iceberg to have a lakehouse architecture, and then we'll get to the workshop. So first, introduction to Trino. I like to call this bring your own data. And so what is Trino? Trino was formerly known as Presto. It's a fast distributed SQL query engine designed to query large data sets distributed over one or more heterogeneous data sources. And there are a number of use cases here that are popular for using Trino. The first one is interactive data analytics. This is by writing your SQL queries either directly to the Trino client or generated by some tool, such as a business intelligence tool, Power BI, Tableau, dbeaver, for example, for a developer tool, and so on. And these queries are run against Trino and returned to the user as quickly as possible. You can do things like testing hypotheses or running A/B testing, or building these visualizations for your dashboards. The next one is being kind of that central point of access in using Trino for federated analytics. So in addition to querying data in the data lake, relational systems or non-relational systems, such as object storage, streaming, NoSQL, and so on. And really, this gives you the ability to be that central point of access and query data where it lives. So, for example, you could query data that may exist in your data lake and join it together with data that may exist in Oracle. And typically, what we see is these are data sources that kind of orbit the data lake. So, the data in your data lake is where your data gravity is, and you're augmenting it with data from different data sources. You can do this all in the same query. One of the sweet spots of Trino and where it was built from the ground up for is running SQL-based analytics on legacy kind of HDFS Hive data stores or object stores itself. Trino's scale and performance allows for analytics that just simply weren't possible before, or they were, but they would take many hours and were very slow. And Trino can do this at a very in a very fast way. And then last is using Trino for batch ETL processing across disparate systems. So typically the data would be loaded into an object storage for your data lake, say S3, for example. And you need to prepare the data to be processed by whether it's your ad hoc users or your BI tools and so on. And oftentimes this is a very resource intensive operation. But Trino can do this quite well, and it's built in a way when running these workloads so it can be resilient to failures and so on. And so for example, let's just say your event data lands as JSON data on your lake. Trino can query JSON, so you can use it to kind of explore and understand the schema, but it is, processing JSON is very CPU intensive, so you do want to prepare the data in something more relational. So you can use Trino to query that data in JSON and land it in different transform steps, and finally until you can get your reporting structure or tables that you want to run your analytics on. And here's a diagram here kind of highlighting what we just described, where Trino sits in the middle. On the top, these are your client tools, whether BI tools or other client support, and the ability to connect into different data sources. So we have our data lakes here. You'll see Tabular and Iceberg on that, and that's what we'll get to in just a minute with our workshop. but also you have your relational databases, your NoSQL stores, your real-time analytics, and other applications. And one thing I wanted to call out, because I didn't mention it earlier, in addition to SQL, you can use Python. We have a Python client to connect to Trino, as well as DBT. DBT is a very popular way for running your transformations, and you can use DBT to power those on the lake using Trino. And if you go to trino.io, you can see a number of users who are using Trino. This is a very small sample, but there are some very well-known companies that are using Trino at scale today. So how does Trino work? So high level, it's a distributed system that consists of a coordinator node and a number of worker nodes. And the more worker nodes you add, kind of the more horsepower you're adding to the system. So it allows you to kind of scale out. And as you add more horsepower, you're going to get your results faster. So you can think of the coordinator as the brain. This is where the SQL comes in. It parses it, it does the planning and optimization, and ultimately schedules the query plan for execution by the workers. And during this phase, it's talking to the data sources about getting metadata or doing security checks and so on. And then when it's time to run, the data is streamed from these other systems. So Trino is a fully pipelined execution engine, and it's processing these in parallel and shipping data across the cluster of machines until it can finally get the results back to the user. So next, we're going to talk about Apache Iceberg. I'm going to hand that over to Tom.
All right, thanks, Matt. Fun quick tip there that Trino is now on dbt Cloud as well. So you can use dbt Cloud for all your transformations with Starburst and Trino. So let's talk about Apache Iceberg. What are table formats? People often confuse this with a file format like Parquet or Orc. A table format kind of sits above that and is a layer of metadata that sits in an object store that allows for a lot of different kind of features that you see more of it like in a data warehouse. So what is a central table storage? So it's independent of compute. That's what central table storage is. And it reduces the reliance on external entities like a Hive Metastore that we've had to use in the past. We heavily relied upon that, especially in the Hadoop world. Access control. So Iceberg usually leaves, not usually, it leaves the access control up to the different engines, how they want to implement it. And then really it just allows for portable compute. So multi-engine. So you have one storage area, and that is usually in your object store. And you have multiple engines that can work on the same Iceberg tables. And also schema evolution. So be able to handle those changes over time, which is pretty common in a source environment. That's where we struggled back in the Hadoop world, was being able to handle different changing columns, different partitions. Iceberg handles all that. So next slide. So the challenge of the Hive connector, I kind of talked about this before, but this was basically in the Hadoop world. This is kind of what we were stuck with, especially a lot of us coming over from a data warehouse world is relied upon everything in the Hive Metastore. That's where all the metadata was stored, all the DDL, the table information and everything, all the statistics. And really the partitions were really limited. You would have to put the partition columns at the end of the table, and you had to make sure that you taught your end users to make sure they put where clauses with those columns. Otherwise, you wouldn't get partition pruning. And so if you're looking at hundreds and if not billions of rows on a query, your query could never finish. And the other thing too, it wasn't really optimized for object stores. So you'd have this column name and an equal sign, and that's not really the way object store works very well. And then also as scaling that thrift service that the Metastore relied upon was really difficult. A lot of our customers that we dealt with, a lot of people that use Trino, really the bottleneck became the Metastore. It wasn't really the object store or a Trino or anything like that. It was really just waiting for that information to come back from the Metastore. So next slide. And so what is Iceberg? It was created by Ryan Blue and Daniel Weeks at Netflix, and they wanted a different way of being able to bring data warehouse type functionality and be able to solve some of the challenges that the Hive connector was providing. So really it was really, and also using open data concepts. So don't create a brand new table, not table format, a file format. Use existing ones out there like Orc, Parquet, and Avro. Those are all open source file formats, and a majority of big data applications use those. And so really in the last couple of years, you've seen enormous interest in Iceberg because a lot of people were getting to a point where they were trying to do GDPR, they were trying to do deletes on data that's in S3, let's say, and then also do updates. There's no way to do that using Hive. You could do it, but you'd have to overwrite massive amounts of data just to do a single update. And if you look in the upper right, I have a diagram in here that shows multi-engine platform. And that's a lot different than what a lot of us are used to in the past, is be able not to allow your data to be locked in. So the data sits in your object store. You have Iceberg, which is just this metadata layer over the top of it. And then you have all these engines that support creating tables, inserting, updating, modifying, and selecting those same tables, which gives you a lot of power. And the current engine support down here, I have it. This is obviously, there's probably another 6 or 7 or 8 or 9 different kind of engines or ingest tools that now support Iceberg. So it's growing quickly, and it's pretty exciting to watch. So I'll get into the architecture. Get into the features and advantages next. So much like a database that I talked about is bringing something called snapshots. So every time you make a change to a table, it creates a snapshot, much like a database table does. And also reduces the meta storyline. So all the statistics and all that information, the metadata is stored on object store, which can be read in parallel. So we're not single threadedly waiting for data to come back from a Hive-based meta store. Also optimistic concurrency. So you can have multiple writers write into tables and trying to figure out exactly what the conflicts are. So that's kind of a database type functionality. Other features like time travel, so be able to query a table that was updated, 3 or 4 updates ago to see maybe it could be an accident, or you're actually looking at what the data was like before the last update. And also schema evolution. So Iceberg tracks all the columns by ID, so you can alter and remove and modify columns on the table just like a regular database. And also something that the Iceberg calls hidden partitioning, and we look at like just regular partition on a table. So you could take any table any column in a table you want to and partition by that, and which is usually like some kind of a time-based field. And users would always be putting where clauses on that field anyway. There's no extra columns that they have to add or worry about adding where clauses to. So all these different kind of features here that you see are more of like if you're coming over from a data warehousing world, that is pretty much table stakes. This is what you expect. And now that's going to be available in a big data on top of an object store. So the next is so more feature advantage. So performance, that's another thing is before we would have to just go into these directories on S3 or Azure or any kind of object store and do these mass file listing to find out what files belong to a table and start reading that. Well, with that metadata layer, it has all the files that currently belong to that table. So there's no listing. You just instantly know what files you need to go read. So it saves a lot of performance. Also, DML, so data manipulation language, so allowed to do update, inserts, and deletes. And this is something that, especially for like GDPR and dimension tables, reference tables, stuff like you couldn't do, that you'd always need to go to like a database or a cloud data warehouse or a regular EDW for that. And also optimization. So a lot of times in the big data world, you're doing a lot of streaming of data in, which makes super small files, and that just kills performance. So being able to do optimization, which means take bunch of those small files and make them larger. And then while doing that, still have read level consistency, meaning end users can still select from that table and not be interrupted while an optimize is taking place. And then also sorted tables, so be able to sort data in these different tables. So when you're reading these tables, you can have increased performance, especially for very, very large tables. And then lastly is vacuum. So you can choose per table how long you want to keep history in each of the tables. So you want to keep, history for 2 weeks, just in case, you can do that. And that's all per table. So, and then the architecture of Iceberg is a diagram on the right-hand side. This could be found on the Apache Iceberg webpage as well. Is basically everything's broken down to these little different layers of metadata. And that allows you to do very, very quick updates and deletes and modifications, and inserts as well. So all you're doing is just adding to these just manifest files. So every time you have a new operation on a table, you get a new snapshot file. That snapshot file points to one or more manifest lists, which points to manifest files. So basically, there's a lot of reusability within the Iceberg architecture, which makes it really lightweight and very, very fast as well. And again, the only thing that is used for a Hive metastore is just the latest pointer to that latest metadata file that you see in that diagram. That's it. That's the only thing that the metastore is used for. So it really increases performance and reduces that single bottleneck for a Hive metastore. So, and go ahead. So combined together with what Matt went through and what I went through, this is really the ultimate lakehouse. And we talk about a lakehouse, we mean a data warehouse and a data lake combined together. So on the left-hand side, I kind of talked about this before, but a data warehouse is, to be able to do ACID transactions and finely grained access control, data quality, performance. Typically, you'll see this in a proprietary system that once you go in, your data is stuck in there. And if you want to use other tools, you can't, or you have to pay twice. And then really it's best for business intelligence use cases. Traditionally, that's what data warehouses were. Now on the right-hand side, you have what the benefits of data lake is the separation of compute and storage. So having your storage and being able to bring different kind of compute to that, or multiple clusters, working against one set of data, and really meant for larger scale open formats. I talked about that with Parquet and Orc. And then structured and unstructured, that's something that a data warehouse typically couldn't do. And then, what is known for data science and data engineering use cases, that's what you'd see a lot for data lake. But now you can combine both of these together, and that's where we get the concept of a lake house. So, and then lastly here, this is kind of where the stack, we like to call it, where it kind of comes together. On the bottom is your object store in any of your clouds that you choose, adding whatever file format that you wish. So Parquet, Orc are very similar. And then you have Avro right in the middle. Avro is a different kind of more of an index type of a file structure. So there's certain use cases that you would use Avro for. And then you have your table format. So table format is not different kind of files, different. It's literally just a layer of metadata. And then you have the Trino compute engine on top. So that really allows you to power your lakehouse and be able to use both Iceberg and your different file formats. And again, it's stored on your object storage. So we have Trino at the top, but there's lots of other engines that you can use that I went over in that diagram earlier. So pretty exciting. All right, now we're going to get into the workshop.
Yeah, so in this workshop, we're going to use Starburst Galaxy, which is our SaaS offering based on Trino, and we believe the best way to run, manage, and operate Trino. And we'll combine that with Tabular, which is a SaaS offering for managing your Iceberg tables, which we believe is the best way to run and manage your Iceberg tables as well. And combining these two products will show you how you can build a lakehouse architecture. So to start, we're here in Starburst Galaxy, and the first thing we will want to do is we'll create a cluster. A cluster is a Trino cluster that we will call demo. We don't have any catalogs yet. We'll do that in just a moment with Tabular. And I'm gonna pick a region. I'm gonna pick my favorite region here in North Virginia, and we'll give it. There are free clusters. We're gonna give it a little bit of horsepower for this demo, and just so it doesn't shut off while we're playing around here, I'm gonna set the suspend time to 1 hour. This feature is pretty neat. If you if you aren't running queries based on any of this amount of time, we'll automatically shut down the cluster for you, saving you on cost. But when you run a query again, we'll wake up the cluster. But just for the purpose of this, I'm going to set it for 1 hour, and I'll create that cluster here. Now we're going to go over to catalogs while that's starting up. And we're going to go to create catalog, and there's a number of tiles here for your data source. We're going to choose Tabular. Now, you can normally use S3, and you can still query Iceberg tables there. But with Tabular, you're going to get the benefit of the managed table service. So Tabular has a variety of features, such as access control at the storage layer, as well as being able to automatically optimize your Iceberg files, and a number of other features as well. So what we'll call this Tabular, and we'll give it a description here. We'll call it Tabular Lakehouse. Why not? And then I happen to have a warehouse in Tabular called Fuller Tabular Warehouse. But I'm going to go hop over to Tabular for just a moment here because you'll see that we need to add the OAuth credential, and I'll show you how to do that. So here I am in Tabular. This is my Fuller Tabular Warehouse, and it consists of a variety of schemas. And when we connect this, we'll be able to access these within Galaxy. But first, what I want to do is I want to create a credential that I'll call, I guess we'll call it Galaxy Tabular. We'll click create, and it gives us this credential here that I'll copy. We'll go back over to Galaxy and we will paste that in. See that there, and we'll test the connection. So the connection test passed, and I'm going to connect the catalog. We're not going to go into role level permissions today, but Galaxy does have a role-based access control system, and you can set various permissions there, but I'm just going to leave the defaults. And I will add this to the cluster we created, demo. Add to cluster, and query my data. And we'll just call this Tabular Galaxy demo. So now that we've added the tabular catalog to the demo cluster, we can take a look what's in here. You'll see that there's some examples, such as New York taxi data. So we can run a query here just to show. Let me minimize this as well. So we can see some data. So this data is actually data that is coming from Tabular. So we go back in here. This was the demo. Sorry, that was the wrong one. Examples, and you can see that this was the table we queried. So what we're going to do is we're going to demonstrate a lot of the capabilities of using Starburst Galaxy in Tabular and how you can use it for your Lakehouse. So the first thing I'm going to do is I'm going to create a schema so we can keep our data logically organized there. And I'll call it Tabular Lakehouse. How about that? So next thing I'm going to do is I'm going to just to keep things simple, I'm going to set my default schema here for this worksheet to Tabular Lakehouse. Now, the first thing we're going to do is we want to create a table. And I'm going to create a table that looks actually similar to the one we queried from examples, and we'll show that in just a moment. And we're specifying the column names and the types and comments with them, and we're partitioning based on month, and we're putting it in the Parquet format. Now, important thing to note is this is an Iceberg table, but the underlying file format is using Parquet, if you think back to what Tom was showing you earlier. So let's run this. And then the next thing we're going to do is we can run a describe on the table to show that it was created, along with the column names, the types, and the comments that were put there. Okay. So the first thing we're going to do is we're going to insert some data into this table. So you can imagine how you may land data into your table, but in this example, we're doing an insert select. So we're inserting into our new table that we just created, and we're selecting from that example. So we're going to treat this example table as our source data, but we're only inserting from data from February of 2019. So let me go ahead and insert that data. So you'll see after running that insert select, it inserted a number of rows. Looks like 7 million rows. But let's just take a look at 10 of them just to get a sense for what's in there. So you'll see that there's some data with each of the column names in the schema. So actually, one thing you will see is we inserted data from 2019, but sometimes some of the data is not from there. So let's take a look. You'll see what I mean in just a second once I run this query. So you'll see here that most of the data came from February. If it didn't, if this was wrong for whatever reason, actually, so what you'll see here is even though we had where month equals 2019 to, that actually is sometimes in this data was wrong compared to what the source of truth pickup time was, where we're partitioning on month. So even though we inserted data accidentally that wasn't from February of 2019, Iceberg still automatically partitioned it. So you can see that there are a number of other partitions that actually weren't from that particular month, but most of them were. So you can see how that automatically did that. So next, we're going to talk about building a reliable pipeline and using the merge command. I'm going to hand it over to Tom to explain this, and I'll drive as he's talking here.
Okay. The next statement should be the deduplicate rows SQL statement.
Yeah, which show that.
Okay, perfect. And then we're going to run that first and just show that this is what we're looking for. So as we move data from our source table into our main Iceberg table, we want to look for duplicate rows and want to make sure that we don't insert duplicate rows into that. So we're going to use this query, but we're going to bury this into a merge statement. So this identifies our duplicates that we have out here. And so this is going to deduplicate everything right here. So now if we run this inside of a merge statement, which Matt will paste into here. So what we're going to do is we're going to select from our source, which is 2019 March. And then we're going to do this merge statement, means we're only going to insert when we have a matched record. And when not matched, I'm sorry, we're only going to insert brand new rows, and that SQL statement above is going to make sure we deduplicate that. The only problem with this is when it says not matched there at the bottom, is we're going to go through all the rows in our target table. And that's fine maybe at the beginning, but as we grow more and more rows into that target table, that's going to take a lot longer to perform. So that took about 27 seconds. But as we grow more and more, it's going to go through all the rows in the target table to make sure we're not going to insert duplicates. So the next statement Matt's going to paste here, we're going to add a where clause to the target table to make sure that we're only going to have a where clause. We're only going to look for what we're going to match. So if we have, like, say, March, we're only going to look for that data. So
yeah, actually, before I do that, Tom, one thing I want to show is kind of the idempotent nature of this merge statement. So you'll see here that this inserted about 7.8 million rows, but let's just say you ran it again for whatever reason, by accident, or your process does that. We'll see that it actually doesn't insert the same number of rows again. So you'll see 0 here, but you can still see that takes some time to run. So let me paste in what Tom was describing here.
And we already have a where clause on the from. So the source table, we already have that, but we don't have it on the target table. So what Matt will paste in is basically a identical merge statement, except for the where clause will be at the target table. There we go.
So what you'll see here is this is where we have our where clause here, and that's just going to make the query perform even more because it's not scanning unnecessary redundant data.
Exactly. We're gonna look at the pickup date time. So, and this is as we grow more and more and more, then it's only going to look at both of the tables out there. So, and this should be 0 as well, unless this is a brand new. Oh, well, we entered a new rows. That's why
It was new rows. Yeah.
Yeah. So now if you run that again, you'll get the same amount, and it should be a little bit quicker because it only has to compare a smaller amount of data on both sides. So it should be about 10 seconds or so. Perfect. 8 seconds. Great. Okay. So then the next thing we'll do is fix existing data. So one thing we couldn't do in the past is update rows of data within a table on an object store. So what we're going to do is we're going to look at trip distance, and we want to round that up because what we're doing is if we're running reports, that is down to a decimal level. So we want to bring that up to just round it up to 1 decimal basically. So go ahead and we'll run that update statement. And, this is something that you could, do in the merge as well. If you wanted to, as you're bringing new data in, you could have that round. So instead of running an update afterwards. So, but this just wanted to show you the update capabilities here. And so now when Matt runs a select statement against that table now, we'll notice that the trip distance is just at no decimal point. So we have 1 and 4. So it's going to be a lot easier to look on a report for that.
Yeah. But what we should have done? We should have showed the data beforehand because.
Oh, that's right. That's a good idea.
But
so what we could do is we can use time travel as part of Iceberg.
Oh yeah,
Trino to look. So we can actually look at the different snapshots that were made to this table using a metadata column called history. So we can run that, and you just put a $ history at. Now we can see all of our different snapshots. So we can see what we did within this table. So we can actually go back in time and look at a previous snapshot and see before that update statement. So any one of those previous snapshot IDs that you can run with a SQL statement. So it's just basically a for version as of on this statement. So Matt will run this, and we'll look at it a couple different merge statements ago that we ran. So we should be able to see that was the data before. So you can go back in time basically and look at data before you had updated it.
Yep. And then one of the nice features of Tabular is you can set how you want your history to be maintained, right? So you can, I believe, tag certain timestamps so they can stay around, but other ones can get rolled off, so you're not keeping the complete history forever.
And then also you can run deletes as well. We won't get into that, but deletes and updates and merges are all part of Iceberg and Trino.
Yeah, I can show a delete. Let's do a delete.
Okay.
Let's see. So in this one, we're deleting where pickup location is 4. So we run that.
And again, when you run a delete, it's very similar to an update statement. You could go back in time and look at those rows before you deleted them, which is pretty interesting.
Yeah,
so now
exactly. So now there should be no data, but again, I forgot to show what it looked like before. So, but if we just run this again, and let's go back.
Put that there. Yep.
Put that there.
Probably change it to a select star. What doesn't really matter, I guess, does it?
Yeah. That should work, right?
Yep.
Oh, look at that. We all make mistakes, don't we? Yeah. Okay. Let's try it again.
I need ChatGPT to fix that for
me. Yeah. So you can see now that because we went back in time, these are the rows that we had previously deleted. But the current time they're all deleted. Oh, great. So thank you for coming to our demo here as we talked about how to build a open Lakehouse architecture with Trino and Iceberg, and using the products Starburst, Galaxy, and Tabular as the easiest way to do that and get up and running quickly.
Thank you.